Hi everyone, and welcome to this week's video on G²CPU. This week I want to do something a little bit different. Instead of having a look at upcoming functionality or looking at the performance gains going from LabVIEW to G²CPU or between the different pieces of hardware, I want to have a look at how G²CPU fits within your data acquisition system. How can you make it all work together? So for this example, I created a producer-consumer loop with a circular buffer. Now, for those of you that do not know, a producer-consumer loop is an interesting concept within LabVIEW and also actually in wider programming ecosystems, where the producer is producing data. It's grabbing data out of our data acquisition device coming from DAC and Max, Visa, third-party DLLs, and so on. And we're sending that to our consumer loop, or even loops, if you want to go a little bit more complex, to do some post-processing on it, get some statistical information, visualize it on the screen, or even just log it into a hard disk. Now, as I said, I made this with a circular buffer, and that's quite interesting because when we have data coming into our consumer loop to do some post-processing on it, we are actually storing it into a buffer, which constantly becomes bigger and bigger, giving us more information on what's going on. Now, this buffer becomes circular when it just becomes too big, and we actually say, okay, from this size, if anything new comes in, just pop out the old one and just release that memory. We're not going to use it anymore. It's stale, it's old data. And just release it so our GPU can use it for our next measurement. And then, yeah, like I said, we just merge everything together and do some statistical post-processing, in this case, on it. Now, having a dive into the code, for those of you that know producer-consumer loops, you probably recognize this. So we obtain a queue, in this case because our producer is simulating data and it's only having one channel coming in. A one-dimensional array is plenty. And also I made it single floating point, or F32, for reasons which will become clear in a moment. Then, jumping into the producer loop, we are simulating via the NI multitone VI a signal. Nice thing here is it's 40 megasamples a second. We're grabbing 4 megasamples every time, and we have a loop rate of 100 milliseconds. Now this boils down, or this gives us a simulated signal coming in continuously at 40 megasamples a second. It also scales up, it scales down, depending on what type of hardware you have. There are optimizations that you can make. But for the sake of this example, this is already a good showcase of how much performance it has. That being said, you will definitely see performance increases with 1/10 or 1/50th of these data sizes. Now, next step is we convert our data to single floating points. Now, the reason for this is, well, my GPU is absolutely terrible with double floating point, or F64 data. I knew this when I bought the system. This is just a consumer RTX 4080 laptop GPU. If you need double floating point precision, if it's absolutely necessary, NVIDIA and AMD and I think even Intel sell graphics cards with perfect double floating points performance. Now, how do you know if your system is capable of doing the double floating points? My personal go-to is the website techpowerup.com. If you navigate there, you go into the GPU database and you search for your specific GPU, which in my case is an RTX 4080 mobile. I can scroll down and have a look at the theoretical performance. This performance is purely theoretical. You will pretty much never reach it, but it's a good indicator of how it compares from one to another, or one GPU to another. Here you can see my half floating point and single floating point, or 16 or floating point 16 and floating point 32, is 24.72 teraflops, which nowadays is absolutely respectable. But if we look at floating point 64, or double precision, as we know it within LabVIEW, it drops all the way down to 386 gigaflops. This is almost 1.5% of the performance. For me, it's fine. If you need that performance, then you don't need to update the program. You just need to tell it, okay, now use double floating points and make sure you have hardware that's capable of doing it. Now, going back to the program. So, after the conversion to single floating point for my GPU, we actually upload it to the GPU saying, hey, please store it in memory so I can grab some new data. Now, the main benefit here is our reference, or our GPU wire, actually isn't a bottleneck. We can make as many copies as we want because it contains a reference to the data, pretty much like a DVR, or data value reference, or for those of you that work in C++, pointers. So it is pointing to a piece of memory. So we can do a lot of stuff with it, and it won't actually bottleneck our system. It won't stop anything. After that's done, we on-queue it at the end, so we can dequeue it in our consumer. So we're just telling the consumer, hey, I have some new data available, which the consumer can handle on its own time. Also have a little error handling here at the end. The main reason for that is just if for some reason the data has been able to be put on the GPU, but we were unable to on-queue it to the consumer, which is also handling the release of memory. We're just going to tell it, hey, just release the memory. We were unable to send it over, just release it. No need to keep this anywhere. And this is great to make sure that you don't have a memory leak as your program goes forward. Then switching over to the consumer loop, first thing we do is dequeue our data reference. So we get our reference, so it's just a number, it's a pointer, it's a DVR, it's just a little piece of data, so we can be quite inefficient with it if we want. And we're just storing it into a circular buffer. Now the circular buffer is just an array of references that we keep on adding to. So yeah, we just push it in every time the array becomes bigger and bigger and bigger until we get an array that's too big, which is handled here. So if the array isn't too big or bigger than a certain size, nothing will happen. However, if the array size is larger than the defined queue depth or buffer size or whatever you want to call it, what's actually going to happen is we're going to pop out the oldest piece of data. And we're just going to tell the GPU, we no longer need this data, we no longer need this memory. Release it, you can reuse it for your next data that's coming in. So we don't have a memory leak and our data nicely keeps on going forward. Now, with all of that done, we have an array of different chunks of data. Now we need to merge it together. Now for that, we have concatenate many in G²CPU. Now this allows us to merge a lot of different signals together, up to version 1.2 and also within version 1.2. This is limited to 10 arrays that you can do at once. Come version 1.3, you can add as many as you want. It's handled internally. This wasn't a limitation of ArrayFire, but we found we were able to circumvent it within G²CPU. Okay, but so with concatenate, G²CPU concatenate many, we can just merge all those arrays with, or all those GPU memory parts or chunks in that array together into one big dataset, one big waveform. Quick thing to note here, almost all functions in G²CPU have auto release, which means after the operation is done, please release the memory of the data on the inputs. Most of the times when you have a cascade of functions, this is fine, this works great. However, in this case, because we have a circular buffer, we want to reuse it on the next iteration, so we're going to tell it, hey, for every array that you put in here, just false, don't auto-release. So that's why we have this little chunk of data here, or this little chunk, or this little algorithm. Now, after that's done, we're going to do some analysis on it. Now, for the sake of this example, I kept it quite simple. We're just quickly calculating a mean value and standard deviation on that entire buffer. And because it's one-dimensional, yeah, there's only going to be one value within this array, so we're grabbing the first index. Now this algorithm, this setup, it actually scales quite well to multiple signals. All you need to do, first of all, is make this a two-dimensional array. So in one dimension you have your samples, and in the second dimension you have your different channels. And then of course your producer needs to have multiple data acquisition parts, which are then merged together. But this pretty much stays all the same, except yeah, you will pull out more samples because the next index will also contain mean values for the other channels. Now going back to the code itself, this keeps on running indefinitely. But once the program stops, we click stop. We tell the program to clean up, to make sure there's no memory leak, that the GPU gets all its memory back to use something else, maybe watch a little YouTube, play some video games at the end of the day, whatever you like. We're going to tell it, hey, we no longer need this memory. So first of all, we're going to release the queue. We get all elements that are still in there. We're going to release those if for some reason the consumer missed one, two, maybe even more elements. If for some reason you were just creating too much elements, or you were doing too much processing, all that data will then, or all that memory will be re-released, as well as a release of the circular buffer, so everything is nicely cleaned up. Now, having a look at the code, this is quite simple. So we have configuration of our multi-tone, so we have frequency of 0, 100, 200, 400 hertz, amplitudes of 1, 2, 3, 4. The frequency 0, it just means DC. The main reason I added this is so that our mean value is nicely linked to it. So as we can see here, if I increase this, you can see the values are updated. But you can also see, because the value changed, you can actually see within the buffer itself, now it needs to change. And this is actually great, because you actually see the transition. It's not just the latest data, but you see how it propagates over time. But yeah, you can play around with a ton of different things. You can increase the queue depth if you want. Yeah. And the values will of course update. So that's it. So I hope you liked this example. It's a nice practical example. I know a lot of you were looking at circular buffers, how to use G²CPU within your actual data acquisition system, so I hope this helps. If you want to know more, if you have specific requests, maybe how to make this work with DQMH or Active Framework or some other framework, please let me know. If there is anything else you want to see, different implementations, different algorithms, always happy to hear them, to get some inspiration for some new examples. And yeah, I hope you like it. G²CPU is free to download for the community edition if you want to use it for non-IP related tasks. The only caveat is you need to upload your code. Otherwise, the commercial license is available. And with that, thank you very much for your time. I hope you find this interesting, and see you next week. Bye.